Can someone tell me if they can see some codes in their screen?
Yes, sir, we can see.
Okay. So in the chats, I have posted a GitHub link, which hosts this code, and I have created a subdirectory called Preschool, where this particular notebook of introduction to PyTorch is given. And when I will go there in the main school and teach the GNN and transformer, all of the codes will be placed in the same GitHub repository. So you can just take a note of that. So I think
Hello, sir.
What happened?
Can you please repost the link on the chat? I actually joined a minute late, so I couldn't find it.
Okay. I have done it again. So did you get it?
Yeah, yes, sir. Thank you.
Okay. Let's start. Okay. So the point of this tutorial is to introduce you with the library called PyTorch, which I will use during the GNN and transformer lectures. Now, there can be some people in the audience who are familiar with this library. And if you think you are expert of PyTorch, you needn't waste this time. However, those of you who are relatively new or haven't done any coding in PyTorch, it's not a bad idea to stay back. Now, maybe some of you are familiar with TensorFlow or Keras. I think those things are introduced already to you over the past tutorials. Now, the point of all machine learning library is essentially to implement the automatic differentiation, which is used during the weight update through backpropagation. And that's the core implementation of each machine learning library like TensorFlow, PyTorch, JAX, etc. So TensorFlow and JAX are by Google, PyTorch is by Meta. So all of these big companies have their own machine learning libraries, and there are, say, advantages and disadvantages of all of them at certain level. But the core concept which goes in are similar for each and every one of them. So nothing big is different. Now, I want you to be interactive in the sense, if you don't understand something, please just stop. Like I'm not following who is raising hand or who isn't. It's just that don't like 5 people at a time open their mic and start yelling. Please don't do that. Otherwise, you can just stop me at any point of time. It's perfectly okay. Now, so let's start. Okay, so the good references are the PyTorch website as well as the GitHub, which I have noted here. So it starts with, like, I think I can safely assume that all of you are familiar with NumPy. If you're not, you're at a wrong place. Okay. So first, just to define like the basic data handling, how to do it in PyTorch. That's the first part of this tutorial. So you can see that the first part starts with basic introduction to PyTorch tensors and comparison with NumPy arrays. And I have intentionally kept this because I expect you to know what NumPy is, how to handle them, what are the properties of NumPy ND arrays. And when we write down data structures in PyTorch, I will always try to draw a one-to-one similarity with NumPy, so that you can just take your intuitions that how it's working. That's the point. So some basic imports, NumPy as NP and at some point of time, we will do some plotting maybe. So we are getting matplotlib, etc.
I have a question. So
Sure.
in the first code, so you have to import OS. I mean, every time you have to import OS, or I mean, this library I am not understanding why you import every time that import OS is.
No, you can sort of off this, but the point I keep it that within some environment, if I want to add additional libraries which are not imported as default, then you can do it like, let me show you that since OS is imported os.sys.path, and this will return you a bunch of variables here. So I don't know if you can see it. Oh, this is like is it connected? I hope so. Can you see the file?
Yes.
Yeah. So I don't know if you saw the output here, but since I'm sharing, it may not be, but you can do like a print statement or something like that, os.sys.path, and it will show you what are the environments are inside it. And if you want to add new packages or environment, you can just add that. So that's the reason. But for this tutorial, it's not important. Where it starts is like import torch. And if you print like torch.version, it will show you what is the version we are using. The latest one is 2.3.1. You may have something installed in your computer. You can also try the code since they are in GitHub. You can directly try them in Colab, where you can use GPUs. Okay. So here, first point is that what is the computational device on which, what's the hardware you're going to use for doing the computations. So there's a line that if torch.CUDA is available, you set the device to the string CUDA, which will check if the hardware has a GPU. If your computer has a GPU, it will use the GPU. Otherwise, the MPS is for Apple Silicon. It will use MPS. Otherwise, if you're using like a regular computer with x86_64 architecture, it will be a regular CPU. So here I'm doing from my own laptop. It's an MPS. Okay. Next, the point is, if you're doing some experiment, you probably want reproducibility. To do that, the right practice is to set the random number manual SID. And since we will deal with both NumPy and PyTorch, so we set the random number backend SID in the following way. So the syntax is like torch.manual_SID and np.random.SID. These are two different syntaxes, for one for PyTorch, one for NumPy. And here we have set the SID to be 42. You could have set it to any arbitrary integer. The integer just refers to a particular state of random number generator, nothing else. Right. Now comes the core concept of tensors. So this is exactly identical to NumPy ND array, and we will here learn what tensor means. Now, when you talk tensor to a bunch of physicists, they start thinking about, oh, some object has like transformation rules as how many indices, that many number of transformation matrix. But in computer science language, an array is just like a tensor. And if you have higher dimensional array, those are higher dimensional tensors. And don't confuse with the notation. Tensor has something to do with coordinate transformation. There's no such thing here. Okay. So I have put some text here, like what is tensor and what is not. So if you have a simple array, it's a 1D tensor. If you have a grid like a matrix, it's a 2D tensor. But you can have any arbitrary shaped tensor, and we will learn how to define it. So just to start from a basic list in Python, 2x2 list, and try to see if you convert it into a NumPy array versus if you convert it into a torch tensor, how do they look like? What are the basic similarities and what are the dissimilarities? So here I have called something, by the way, do you see my cursor here?
Yes.
Yeah, okay. So I have defined a basic list, like 2x2 sort of matrix with the entries 1, 2, 3, 4. Now I can wrap it by the function torch.tensor, and then the x data becomes a torch tensor. And if I like wrap it with np.array, it becomes a numpy array. Okay. And it's very easy to convert a numpy array to a PyTorch tensor through this syntax torch dot from numpy. And if you pass a numpy array, what it will return is a PyTorch tensor. So this is an example is like NP array was a numpy array, and X data NP, it's a torch tensor, and you can see it has just converted it. Similarly, the old array type, the data type was numpy.nd array. So from this one function, inbuilt function, from numpy, you can convert a numpy array into PyTorch tensor. And identically, you can, so here, X data, which was a torch tensor, if you call it with a keyword .numpy, you can convert a torch tensor to a numpy nd array. So these are some small little tricks, good to know. Then there are some inbuilt function of creating arrays with fixed entries. So you can use this things like torch.zeros, torch.ones, torch.rand. So all of them take some shape. And if you do torch.zeros of that shape, it will create a ND array, like a torch tensor, all with elements 0 of a given shape. Ones will create an ND array with all elements 1 with a given shape. And randn are like random numbers filling the torch tensor elements for a particular shape. Okay, so let's do this. Torch.randn 2, 3. This gives you a 2x3 matrix with random number as entries varying from the range 0 to 1. And you can always use similar syntaxes in NumPy, where the syntax would have been numpy.random.normal equal to, with you have to specify a shape like size equal to 2, 3. Here you can directly pass it. Okay, so these are the sort of comparison among the syntaxes. Right. So now let's use the keywords torch.rand, torch.ones, and torch.zeros and create tensors using this key functions. So you can see torch.rand returned you 2x3 tensor with random entries. Torch.ones returned you all ones, torch.zeros returned you all zeros. So it's just doing its work, and instead of writing a matrix by hand, you can use these functions which are much faster in operation. Cool. Now, once you have learned how to define variables and how to define basic tensors, you need to do computation with them. Otherwise, what's the point? So let's try to see how you can do some basic algebraic operations using the torch tensors. So of course, you can do operations if they are of similar shapes and size. So you have defined two different torch tensors and let's call them x1 and x2. And torch.friend is 2, 3. Torch, both are 2, 3 tensors. You can print them and you can add them, y equal to x1 plus x2. And once you do that, and if you print it, you will see x1 and x2s are two random tensors, but their elements are element-wise sum of x1 and x2. So any basic algebraic operation happens element-wise. That's the takeaway message. And here, since we didn't define any device for x1 and x2, the default device are CPU. And if you add two objects on CPU, the new object gets created on CPU. And that's why y.device returns you CPU. Okay. Similarly, now, given something is on CPU, how do you put that data object on GPU, MPS, or different hardware? So here, if you remember correctly, device was said to be MPS because Mac has MPS. You can have dedicated GPU, which will turn out to be CUDA. So if you do some old y.2 device, and the new y1 will live on MPS. So this is how you convert a tensor living on CPU to a tensor living on CUDA or MPS. Okay. Right. So let's do a bit more algebra with the basic tensors, and then I will take a pause to take your questions. So again, let's define some data. X data, if you wrap it with torch tensors, it's created on CPU. The other way to create a variable directly on MPS or GPU is that you call torch tensor, but pass a keyword argument device equal to the device you're looking for. And there can be multiple devices. There can be a multi-GPU system and things like that. So you can place your data variable on a particular device, and you can specify which device you're passing. And by default, like if you do it in a default way, it will be on CPU. But if you use this keyword, it will be on the desired hardware. And if you define two variables, both on a particular hardware, then the output, when you combine them, will be on the same hardware. And remember, if you have x1 on CPU and x2 on GPU, you can never combine them. You can't do algebra with two tensors which are living on two different hardware devices. Okay. Right. And finally, the addition can be directly implemented through this keyword underscore. So if you ever have like two variables, x1, x2, whatever be it, and specify an operation here, addition underscore x1, you can see x1 sort of remains unchanged, whereas x2 gets element-wise added. So if you don't want to use like x1 plus x2, which may be a bit more time consuming if x1 and x2s are very large, then what you can do, you can directly do this operation x2 dot add underscore x1. And this will ensure that all the elements of x1s are added to x2, but the elements of x1s are unchanged. So this is just to introduce you with some basic algebraic operations of what and how you should do it. So before I go to next set of topics with the algebra and process of torch tensors, do you have any question?
Sir, can you hear me?
Yeah.
Sir, I have a very small question. As you discussed that if we have, let's say, one variable x1 and another variable x2, and let's say x1 is on CPU and x2 is on GPU. So you emphasize that we cannot do any arithmetic operations. So
Correct.
it looks very obvious. But my concern is, are there any operations, people do where you have one object on CPU and other object on GPU, something like
No,
that?
normally the practice is if you find something is on CPU and another thing is on GPU, you bring it both of them to the same hardware and then do the operation.
Okay. Yeah. Okay. Okay.
Okay. Any other question? Good. Let's move on. Now you have learned how to do like basic addition and things like that. You can check the manual how to do multiplication and subtraction, not a big deal. Now, a tricky part to learn is how do you play with the shapes of the tensors. They play a big role that how do you reshape or change shapes of a tensor. So the way is one of its like view. Okay, so let's say you have a 4x4 matrix, random number, torch.random 4,4. So if you see the size and shape, both returns you the same number. Now you want to flatten it. You have a 4x4 matrix, you want to flatten it, and you want to get a single row of size 16. So you can just, how will you do it? You could have done dot reshape 16,1, or you could have done x dot view 16. So this will convert all the 16 numbers as one row. And you never have to do this operation by hand. There are inbuilt functions to do it. Then there are, if you want to convert it into a 2x8 sort of matrix, then you can call this like x dot view -1, 8. It will ensure that the last dimension is 8, so the other dimension can only be 2 because total number of elements are fixed, and it will convert it into a array of 2,8. Okay, so you can just print it, and you will see that whatever was here, like this 4x4 has become 2,8. Just let's try to see the first element 1.57 blah blah blah. The same thing remains. The 8th element, which should be -0.6581, that has come here, and then the 0.0499, which has appeared here, and the last element 0.0360, that's appeared here as the last element. So this is a nice little tricky way that you convert a 4x4 matrix into 2x8 matrix by one liner, and that's the view -1, 8, where the role of the -1 is telling that the last dimension of the output matrix should have size 8. So automatically the first size is fixed to be 2. Okay, so that's sort of nice thing. Now let's come to higher dimensional tensors. This is where non-trivial stuff starts getting in.
Hello.
Yep.
Sir, what would happen if I write 2,8, not
No.
-1,8?
No, 2,8 means you are having a tensor which has shape 3, and then at least the third space have 8 elements, but your original matrix don't have that many number of elements, so it should throw you an error. Okay. So you can just do like a dot x.view and put double question mark and enter in notebook. And that can show you that what are the properties of this key function called view and how does it work. I just gave you an example, and you should try to dig it out. It's very trivial. If you don't find it, catch me in the main school in person. Right. Now, let's create a rank 4 tensor. In our physicist language, a computer scientist would have called it 4-dimensional tensor. Torch random 1, 2, 3, 4, which means you have a tensor whose 0th dimension has dimension has only one number. The first dimension has 2 numbers. The second dimension has 3 numbers, and the third dimension has 4 numbers. You can just put arbitrary integers here. And if you put a dot size, then it shows A is a tensor of size 1, 2, 3, 4. Now, the interesting part, all of you know about matrix transpose. But for a higher dimensional tensor, you can take any pair of dimension and can swap them. So that's the generalized concept of transpose for high dimensional tensors. So if we take this high dimensional tensor A and say we transpose it 1, 2, that means here in Python, the indexing starts with 0. So 1 refers to the second dimension and 2 refers to the third dimension. So what I'm telling this through this operation, that take the tensor A and swap its second and third columns or rows, like the dimension, second and third dimensions. And once you do that, the output tensor has a shape 1, 3, 2, 4. So this 2 and 3 have been swapped. So all the numbers which were appearing in the second and third dimension, they exchange locations. That's how you do the transpose. So we all have learned about matrix transpose, but the same concept can be smoothly taken to higher dimensional objects. And then the core concept of view, which we discussed a few minutes back, that can also be brought to higher dimensional tensors. And if we dot a dot view 1, 3, 2, 4, it just does nothing but keeps the 1, 3, 2, 4 size. But you can also swap 2 dimensions using a view command with specifying the dimensions. Okay, so I have kept a few more examples in the notebook. I encourage you to go through them. And here we see like what are the basic code difference between a transpose and a permutation. Like if you have a higher dimensional tensor, you can also take 2 dimension and permute them. So are there differences between like swapping 2 dimension, calling it transpose or calling it permute? So there are many possible operations here, and it's good to understand in which case, which of these operations are more handy. Okay, so here I have given that permute 1, 0. So let's take a particular example. Let's say X is just an array. It's just the A range 6, which means it will have element 0, 1, 2, 3, 4, 5. This is the array. Now, if I do X view 2, 3, then I'm just converting a length 6 object into 2 by 3 orientation. So it just it just orients it like 0, 1, 2, and 3, 4, 5. The elements are now 2 by 3. Now, if I permute or transpose 1, 0, that means this is a 2-dimensional object. So I'm just swapping one of the dimension with other. And once I do that, you can see a 2x3 object becomes 3x2 object. Okay, so you can just do a permute like this. So it's good to know how do you do these operations. Now, so until now, you have learned how to define objects, high-dimensional tensors, and how to do basic algebra with tensors like addition, etc. But now we will try to learn how do you at all multiply them when they're complicated high-dimensional objects. And there is a concept called per batch multiplications. So we will go into them. So before I move on, any questions? No. Good. So the multiplication in PyTorch is like can be done in many ways, but it's good to know different syntaxes, their basic differences, and where they perform equally. So this @ symbol refers to matrix multiplication in NumPy as well, and you can do that. The alternate one is torch.mm. So this performs matrix product over two matrices, but it doesn't support broadcasting. So we will later understand what does it mean to broadcast a tensor. A handy way, now matrix multiplication, all of you know what the shape of the matrix will be. Like if you multiply ij with jk, the output matrix will be ik. There is a cool notion called batch matrix multiplication .bmm. So let's say there are two tensors. One is of shape like b cross n cross n, and other is the second tensor of shape b cross m cross p. So if you take these two tensors where b refers to the batch size and performs a BMM, then the output tensor will be b cross n cross p. So it will do the matrix multiplication over the third dimension from the first tensor and second dimension from the second tensor. The dimension along which the batches are defined will remain untouched. Okay, so this is a cool notation where it actually does matrix multiplication for per batch element and then stack all the matrices together. But if you try to do it by hand, it's a much more time-consuming operation compared to when you call this keyword function .bmm. Keep this in mind. So instead of @, we normally use this torch.bmm or torch.matmul, matrix multiplication. So that's how you multiply matrices here. Okay, so here what I did is to define a variable x of shape 2, 3 and w, which is like a tensor of shape 3x3. So if you do an x a times w, you get 2x3. And if you do matmul, you also get the same output tensor 2x3. Okay, so this is just to demonstrate you that the default matrix multiplication @ and the new way, the new syntax, they're exactly giving the same number. They work similar ways. Now, here, there can be a third way. Okay, batch matrix multiplication, which I just told you. So I have defined two matrices of batch size 10. One is 3x4 and another is 4x5. So this shows you when you do a batch matrix multiplication mat1 and mat2, the output shape will be 10, 3, 5, which is what you get. Now, in both NumPy and PyTorch, there is another cool way of einsum. I absolutely love this. So this is like made for physicists. We love dummy indices. We have lower and upper indices repeated contract. So let's say MAT1 has indices like Pij, and matrix 2 have matrix like indices Pjk. So if we define a contraction rule that you take MAT1 and the element Pij, and from MAT2 take the element Pjk, sum over the j labels and produce Pik with this string. And if we pass the two matrices MAT1 and MAT2, you can verify that the P label remains unchanged, whereas like J and I are the output shapes, whereas the K gets contracted. Okay, so this is another way of doing batch matrix multiplication. In fact, the einsum is a way, like if you have 30-dimensional tensor and 35-dimensional tensor, and if you want to do contraction or tensor products of one or few more dimensions, then einsum is the right way to do it in Python. Now comes the core concept of dynamic computational graph and backpropagation, where we gradually gets into machine learning. So any questions with like tensors operation, matrix multiplication, batch matrix multiplication, einsum, how they're working, etc.? Everyone is clear with everything? Okay. Very nice. So now we come to the concept of dynamic computations of graph. And this is not GNN. Like any computation inside a computer have a dynamic computational graph, and we will see how it works. Okay, so let's see what it is. Now, when we could have asked, can we do machine learning with NumPy only? Theoretically, the answer is yes, but the core point is that when you do a machine learning, you do backpropagation and weight update. And for that, you really need to compute derivatives of functions with respect to the weight parameters. Now, all these functions can be arbitrarily deep and complex. So you don't know a priori how to compute derivatives of them with respect to the weight parameters. For that, the Autograd thing works, and we will try to understand how Autograd is used inside PyTorch to compute derivatives of a function with respect to its parameters automatically. Okay. So let's say our neural network give output a single scalar value. Scalar here means just one number. We would talk about taking derivatives, but multiple output variables, values, taking the derivative becomes harder. So let's go to the core concepts that you have an input variable X. And let's say you define it, we will see how to do it, but if you define the variable X with a keyword requires grad true. What's the advantage of declaring the variable X with this keyword? That if in the downstream task, if you have a function f of X, then automatically computer stores the number df dx. Okay, so here we will try to demonstrate this fact. Let's say we declare a variable X equal to something. You can do torch.once, torch.random, doesn't matter. And if we require that, if we see X dot requires grad, it will return false, which means computer doesn't know how to compute derivative with respect to x. However, let's say we change that keyword, requires grad to be true. And then computer knows that if in down the line of computation, if we define some sort of function f of x, then it will be able to store the derivative of f with respect to x. Okay. So we will do it here. Let's say x is a variable. So let's say x is sort of a vector, 3 numbers. And then y is like xi plus 2 whole squared plus 3. So we will use x equal to 0, 1, 2. So x0 is 0, x1 is 1, x2 equal to 2. And we have defined it with the keyword argument requires grad true. So that's x. Now we will compute few quantities, a, b, c, as a will be x plus 2, b will be a squared, which is x plus 2 whole square, c will be b plus 3, which is x plus 2 whole square plus 3, and y is c dot mean, which is this formula, y equal to 1 by length of x times sum over the whole thing. So when we could have written down x equal to this tensor and y equal to say x plus 2 squared plus 3 dot mean. But what computer actually does, it splits the whole task in few steps. It first defines a variable a, computes the square, adds a 3 and takes the mean. And we see that what the output are. Now, the interesting thing which I want to show you that at each computation level, the tensors a, b, c, y, z, a different kind of gradient function is stored with the computer. What's happening that since we have defined x, the tensor, basic tensor, with the option requires grad true, so a equal to x plus 2, a is a function of x, then b is a square, and since a is a function of x, b is also a function of x, c is also a function of x, same can be said for y and z. So since x dot required grad is true, and we have made this computational flowchain, then the derivative of z to a all are stored inside computer. And this is guaranteed because all of these variables have a particular grad function. So if we call, let's say, x dot grad, now that will contain dy dx. Okay. So how do we know computer has done the right thing? So if you, first of all, why 3 numbers? So x was actually 3 numbers. So y dot grad returns you actually del y del xi. Okay. Now, if you really want to compute it by hand, you could have done del y, you could have used the chain rule. And you know that the relations which we have set, let's say del y, so del c del b is 1, del b del a is 2a, and again del a del x is 1. So we can use these chain rules here, place them, and verify that the gradient what computer returns you is indeed the variable, the gradient which you would have computed with a pen and paper. So I encourage you to do that. The numbers which they're returning, like for if x equal to 0, 1, 2, given the y is a function of x through a series of computation, del y del x is stored. Okay. And similarly, you can get the derivative of all other functions which are there in the computational chain. So this is a very important concept that given you define a tensor which requires grad true, if you build a function which is a function of this tensor, the derivative of the function will be automatically computed. Now you could have said, what's the point? I can compute this by hand and compute the derivative myself. But sooner or later you will see that we will start dealing with complicated objects called deep neural networks. And for those with million parameters, it's impossible for a human being to sit down and compute derivative by hands. And in those cases, this built-in Autograd functional comes to rescue. That computes the derivative. Those derivatives are used for backpropagation. So tell me if this concept is clear or not. Do I need to explain something? This is an important concept, that how Autograd works and how the derivatives are stored.
So
Can you
in a way, when we want to access these derivatives, let's say what we need to write y dot x dot grad or y dot grad, right?
Yeah.
Okay. And this is useful because every time we don't need to like go the chain process, right? It is
Right.
on a go doing it.
You never need to compute this chain rule by hand. It will do it by itself. If you have a deep neural network, let's say 100 layers deep, then will you and say 10,000 parameters, then are you going to compute 10 to the power 6 partial derivatives by hand? The answer is no. The computer is smart enough with a built-in Autograd function tool, which will do it for you.
Oh, actually, my question was that like why this is done on a go, right? On a go in that sense that on from the first we are like telling that this grad thing is true, and then on a go it is storing something. Let's say for each function it is storing its derivative. So
Right.
like there, but like even if in computer we can do this derivative by some defining some function, derivative function, right? So
First of all, here there are smooth functions and you know how to compute derivative. Let's say del B del A, you know that is 2A. But if it's a multi-layered perceptron with some complicated intermediate layer, you don't know the mathematical rule of how to take a derivative of an arbitrary function. You can compute derivative only of known functions. Right?
yes,
If
yes.
If someone tells you how to take derivative of sine x, you know it cos x. But if you get a very arbitrary complicated function which doesn't have a closed analytic form, then you can never compute derivative of it. Whereas if there is an inbuilt Autograd functional, whatever complicated function it is, even if it's not analytically defined, it can compute derivative of it numerically.
Okay, okay, okay. Got it.
Sir, I have a question.
Go ahead.
Okay, so if I put x dot grad,
Mhm.
it is returning dy dx. Why is it not returning dz dx or anything else? I
No. So you
mean, we
can.
have put z equals to yq as well.
Right. So you can define what, which variable it will compute. So here I am just showing you like what will be del y del x. But there are other syntaxes to figure out like what will be said del z del x, etc. That we will discuss.
Sir, so a small question. So, when we initialize this Autograd function, so after making it true, so in computer, whenever we define the function, at that moment, it stores the derivative of the function, or is it calculating on fly or something like that?
No, so the derivative are actually like there is a keyword called dot backward. We will see that to access all those derivatives, you need to really call the backward functions. But they are dynamically stored through memory allocation. But if you want to access them, you need to call a keyword dot backward, which I will give you an example.
Okay, okay.
Right. Let's go ahead. Now we will use this Autograd to compute backpropagation. Now comes, let's say we have a composite function. We have a function with two parameters, W1 and W2, and the output is W1 acting on X, followed by some activation function that can be like something like ReLU, sigmoid. Those activation functions are essentially like ReLU is chopping off the negative numbers, and there can be tan hyperbolic, things like that. But let's say we have a functional forward computation rule that given two tensors W1 and W2 and an activation function sigma, how do we compute Y prediction given an X? Okay. Correct. So we have defined some dimensions, and X and Y are two random numbers. Let's say W1 and W2 are also random numbers. So we will first see how to compute this function. Let's say an intermediate latent variable H is X dot matrix multiplication of W1. So this is H is W1 times X. The output H ReLU is when you suppress all the elements which are negative, which means if some number is negative in H, you set it to 0. And if some number is positive in H, you keep it as it is. And then the output, which is here H ReLU, is corresponding to sigma operating on W1X. And the Y prediction output is H ReLU matrix multiplied by W. Okay, so once you do this Y prediction, this is analogous to W2 acting on sigma of W1X. Now, there is something called a loss function, which is like a distance between two numbers or two tensors. So let's define a loss function. Loss is Y predicted minus Y square of it, and then you take a summation. So first, you should realize that Y prediction is a function of W1 and W2. And so here, Y prediction, which we have computed, is a function of W1, W2. So the loss is also a function of W1, W2. Now we have not initiated X with a requires grad true. So it by default doesn't store the derivatives. So for that, we have to compute the derivatives by hand and do the backpropagation. So how do we do it? If a loss function is Y predicted minus Y whole square, then the derivative of that quantity is 2 times Y predicted minus Y, and Y predicted is a function of W1 and W2. So gradient with respect to W2 is computed, and gradient with respect to W1 is also computed. Now, here you see that once we compute all the derivatives by hand through these 4-5 lines, only then we can do a backpropagation that and update the weights that W1 is old W1 minus a learning rate times del L del W1. So you know that if you have done some very elementary machine learning, that the core part where the weights are updated through this backpropagation, that new weights are old weights minus the derivative of loss with respect to the weight parameters times the learning rate. So you see, if we don't use the Autograd inbuilt, for simple loss function, we can still compute the derivatives by hand and can do this backpropagation. And if you run the notebook, you will see that the loss is decreasing and a learning is happening. But we don't want to do this by hand computation. We want to really use the inbuilt Autograd. So for that, we try the following. We create the model. Okay, so whatever this W2 sigma times W1, this we will use write down as a model. So here, everything in PyTorch, the neural networks are inside this nn.sequential. So what we do, the first linear layer, W1, is defined in this way, torch nn.linear, and the activation function is ReLU, and the W2, okay, so this one should be actually W1, and this one should be W2. The core takeaway point is that when you wrap it inside an nn.sequential, the weight parameters are automatically declared with requires grad true. So if model is has weight parameters, those W1 and W2, in the previous example, the requires grad was false because we just defined them as regular tensors. And that's why we had to compute the derivatives by hand. Here, we wrap it under nn.sequential, and that what ensures that all the weight parameters will be declared with requires grad true. And we define a loss function, which is mean squared error loss. And what we do, that we compute an output, compute the loss function, and we do a backward. So see, the whole process of computing the derivatives at each step of computation is totally gone now. Why? Because we already know the parameters are defined with requires grad true option. All we need to do, that we know by construction, this loss has float like access to the derivatives. So when you compute loss dot backward, it computes the derivatives. Like del L, del W's are accessed. And you can do it through param.grad. So model.parameters returns you all the weight parameters, and param.grad is derivative of the loss function with respect to those parameters. And you update each weight like the weight minus learning rate times the derivatives, the gradient. Okay, so this is the first way you do learning, statistical learning, that you have defined a model using nn.sequential, which is the core library inside PyTorch. It makes the weights updatable. You have used the loss dot backwards to use the Autograd to compute the derivative of the loss function with respect to the weight parameters, and use them for the weight update methods. So this is the first step of learning, and the same learning which we did last time by doing explicitly everything by hand. This is the one we are doing using the Autograd backpropagation. Okay, so this is the code change when we use the backpropagation. Now we will try to use this example to bring another concept called optimizer. But before I move on, I want you to appreciate and think for a minute that what are the advantages of going from by hand computation of derivatives versus using the Autograd, where the derivatives are automatically computed and you can use them for backpropagation. Okay, so any questions on that? The same example solved using like computing the derivatives by hand versus using the Autograd inbuilt functional and you exploiting it to compute the derivatives. Any question on this? I strongly encourage you to run this notebook. It should run out of the box. Okay. So since I didn't hear anything, I hope there aren't any questions. Okay.
Can I ask one question, sir? Not related to this appreciation of the derivative, but actually you said to run and check it. So I see, sir, you are running VS Code and and in that you just open the notebook and you have start running, or you may need to load some PyTorch environment or something. Can you show us how you are running it?
So like PyTorch is installed in my computer. So when I choose Python as my working environment through some Miniconda, it has all the softwares installed.
Okay, so I understand. So first you load your Conda environment, and inside you already have this VS Code, and using that you launch your notebooks. Okay,
Absolutely.
thank you, sir.
Okay, so now we will.
Hello.
Yeah.
Hello. Can you please comment on that, how this learning rate is related to the randomness of the loss with epochs? With epochs
No,
means
learning rate, at first go, we are using it as a constant number, a small number. Later, we will see that we can use dynamic learning rate, that based on how much learning steps we require, we can change the learning rate with epoch. So there are concepts called learning rate scheduler, which we will use. But for the time being, learning rate is constant, a small number for each and every epoch. Okay.
so. My question was that does the way you have told, it is by doing that it helps to do the it helps to reduce the randomness in the let's say training loss curve, or like that. Randomness means I am trying to say fluctuations, that we get sometimes fluctuation.
No, so the fluctuations depends on quite few parameters. Learning rate just decides how fast or slowly you go towards the global minima of a loss function. Now, if the learning rate is too small, you may take very large time in order to converge with the training, whereas larger learning rates lets you converge faster. But on the other hand, you sacrifice at the point that you may not actually converge at the rock bottom of a steep uh, loss manifold. So you may just fluctuate. So that's why people use learning rate scheduler, that after a few steps, people tend to decrease the learning rate so that you reach towards the minima faster, but then you convert slowly so that it's ensured you have reached the right global minima in the loss landscape. Okay.
Yes, sir.
Okay. Great. Now, we did the learning rate change, this parameter update by hand. The gradient computation was done automatically. But this thing is also made automatic inside any machine learning library. And in PyTorch, that's called optimizer. So here we see that when we declare that optimizer is something, let's say Adam, there are many optimizers, each serving a different role. We pass model.parameters and a learning rate equal to learning rate. Optimizer.backward, the zero grad just cleans the state from old gradient computation. Loss.backward lets you compute the derivative of the loss function with respect to the original parameter at its step of computation. It computes the derivatives. And when you do optimizer.step, it actually computes the it accesses the computed derivatives and does this process. So it has access to param.grad. It knows a learning rate. So it just does the weight update. So that's the point of optimizer.step. Okay, so what you learned is that how first you roughly define some model which is flexible to define Autograd. Then how do you compute the derivatives efficiently? And then how do you update the weights efficiently? So there are three parts: the model declaration, the Autograd part, and the optimizer part. This will all play their individual role in the training dynamics. Okay. Now we will go through a bit more through actually the nn.Module inside PyTorch, which we always use to declare neural networks. Okay, so this is a new ball game starting. Everything, when you declare a neural network inside PyTorch, you can read the text later. I'm not going to read the same text which I have written. It's coming from a class called nn.Module. So all neural network should be inherited from nn.Module. And it should have a basic skeleton that it should have the constructor through init, where you really define some global parameters and the weight parameters of a neural network. And the forward is the key function where the forward computation happens. If you say my neural network fx takes x as input and gives me output y equal to fx. So this is where you pass the x and the neural network returns you fx. So this is the core structure you should keep in mind, that all neural network functions has to be inherited from the class nn.Module. All the private weight parameters should be here under the init. It's the constructor. And the forward computation happens inside the function forward. Okay, let's keep it in mind. So let's define a simple classifier. We want to classify a few things. So here we have defined something like my module. So the syntax which you use, you declare a neural network like calling the function and do the forward passing. You give an input x and ask for the output as nn of x. Nn is this function. And whenever you will call for nn(x), it will actually do the forward computation. It will execute the forward rule here. Okay, so let's go through this simple classifier. Let's say this is a neural net. This is a kind of picture all of you see all the time. So this is a neural network layer, which should be like my module. X is the input. The forward computation will happen here, where it will use its weight parameters and convolute the x's and give the output y. Okay. So let's define a simple classifier, something like a simple neural network module with 2 layers and 1 activation function. How do we do it? So you see the simple classifier, again inherited from nn.Module, has 2 intermediate layers, like a linear layer which does linear operation. It has weights and bias. So nn.Linear is the syntax of a linear layer. There is an activation function, nn. Like tan hyperbolic activation function. You could have defined your own favorite activation function. And now how the forward computation happens. So the input x goes through first linear layer. The output of first linear layer is then filtered through an activation function. And that filtered output is again gave as input to the second layer. And finally, you get something which your forward function returns. So if I have a simple classifier like this, and it's flexible to give you the hyperparameters of these modules through num inputs and num outputs and things like that. Then what it will do, it will create these weight parameters and compute, like make the forward computation. And if you think that where are my weight parameters, the weight parameters are in linear 1 and linear 2. Okay, so let's try it a little bit. So I have given like 2 number of inputs, number of hidden layer 4s, so hidden features like the latent space here. What is the dimension of this? We have given it to bit 4. And if we print the model, you see there it's showing that there are 2 linear layers and 1 activation function, tan hyperbolic. And model.children lets you access the intermediate layers. And there are ways to access the weight parameters directly. So you can do this model named parameters, then you can have like a pair of data, what is the parameter name and the parameters, and you can directly access them. So if you ever wondered that I have a trained neural network and how do I directly access the weighted parameters, you can easily do it here. Now, we learned that how do you create a neural network, but another important part is to create a data set, because most of you are probably high energy physicists, you will have data from high energy physics, and how do you like customize it in order to use it for a neural network training? So for that, PyTorch gives you a customized data class. The data class is again like inherited from inbuilt structured data set. So what are the 2 key points? The length of the data set will be returned by this key function with __ length. And what will be one instance of the data set is returned by this get item function. And see, these key functions are always with this double under, they're called dunders. So when we set up a classification task, you always have an input and a label, right? So here we see we have a data point and a label corresponding to it. And each get item is returning a data point and a label. Right, so let's try to see what these data points are. Essentially, I have put here some plotting to realize what these data points are. So if you see it, there are 2 sorts of data sample, like 2 class. One is this blue class and one is this orange class. And X1 and X2 are the features. So depending on where these data points lie, if it's lying along this diagonal axis, then it's labeled as class 1. Whereas if it's along this diagonal axis, it's called label class 0. So the learning task which we are going to set up is to classify a data point, which class it belongs to, based on the coordinates of that point in this plane. So this is important to understand for any machine learning task, is that what is the statistical learning task you're trying to solve? And here, what we are trying to solve is that from the location of the points, we will try to figure out whether the point belongs to class 0 or class 1. And the dataset class is essentially here. The data point gives you the position vector in this 2D plane, whereas the data label returns you whether it's a class 0 or a class 1. Okay, so is this clear? What is the statistical learning task we are about to solve? Like, we want to find out a neural network which should efficiently tell us based on the location of the points, whether the point belongs to class 0 or class 1. Any questions? Good. So once we have done building the data set, there is a concept called data loader. So here, what we want, you saw that get item returns you one instance of a data set.
Hello.
Yes.
So I have a question about that sample visualization.
Yeah.
Yes. Here, I mean, how is the decision boundary drawn that this segregated the class like this?
So we don't have a decision boundary yet. We want the neural network to figure out the decision boundary. We have just created a finite sample and located few points along this diagonal and called it class 1, located few diagonal points along the other orthogonal diagonal, called it class 0. And now, in the absence of a decision boundary, if we feed these points into a neural network, can the neural network figure out a decision boundary of its own? Instead of a human being sitting and drawing the decision boundary, can a neural network do that job? That's the statistical learning task we are after.
Okay.
Okay. Now, when we do a training, there can be some inherent fluctuations in data which can reduce the performance of the training. So we don't train per data and feed it to a neural network. What we do, we take a chunk of data, we make it a batch and feed this batch to a neural network so that if there are some sort of bias in any of the data point, the neural network can get rid of that bias. So how do you batchify it? And for that, PyTorch gives you a thing called data loader. So data loader, what it does, it takes the data set and you pass a batch size. What it will ensure that it creates a few mini batches where each batch will have size of the number you have specified. So here the data loader will be like those points, but 8 points at a time. And if you do a shuffle through, that ensures that all the points are randomly like jumbled. And it's not that only points from one data class will be inside a batch. All you know that each batch will be of size 8. This can be any other number. So when we do a data loader and data label, so once in instance of the inputs, so one data, the input was the 2-dimensional number. And once you have made a batch size of 8, you see it's a data of 8 pieces of data, each with 2-dimensional numbers. So this tells you that it has clubbed few points together. And if you try to see what are the labels are, you see there are mixtures of zeros and ones. So it has taken points from both the class 0 type, class 1 type, taken together and randomly shuffled them. And if you do this next iter data loader once more, you will see another orientation, another instance of data set. Okay, so this is a way how you batchify and form mini batches of data, which you will put to a neural network. We have already talked about optimizer, and for classification losses, let's do like, we only have 2 classes here, class 0 and class 1. So for that, we will use binary cross entropy. Okay, so this is the formula of binary cross entropy. And sorry, there will be Y hats here. I've put the formula something wrong. I will correct it. So let's see how do we do it. Like we have a loss function, which is binary cross entropy loss. We are using a optimizer, which now I have chosen to be stochastic gradient descent. And now let's set up the training. So I have that training data set of size 2500 points. Okay. And I have built the data loader where each batch has 128 points. Now let's put a simple classifier. So we had that model defined, which were two linear layers, and in between an activation function of tan hyperbolic, which was sitting. Now, a thing to remember that when we train, we have to set the model in .train mode, which will ensure that all the weight parameters are updated. Whereas if we set it to .eval mode, then the weight parameters will be frozen. Okay, so how do we write the training loop? It's good to keep an eye that we loop over the epoch, and for each epoch, we loop over all the mini batches coming from the data loader. We put both the input and target on the device where we want to do the computation. We compute the forward passing. This is analogous to like computing f of x, where f is the neural network. And then we compute the binary cross entropy loss. Now we go back to the optimizer, get rid of any old derivatives, and then we call loss.backward. So this computes the derivative of the loss function with respect to the weight parameters. And once you do that, we call the optimizer.step. So it uses the stochastic gradient descent, it uses the learning rate, it already has access to the derivatives of the loss function with respect to the weights. And what it does, it just changes and updates the weights of the model. Okay. So here you can see that I have run a full training on my laptop, the MPS device. You are welcome to try on your laptop or on Colab. And you can see that slowly the loss is decreasing and it's going somewhere. Okay, so I have ran it for 100 epochs. It started with a loss value, training loss value of 0.71-ish, went down to 0.02-ish. So it's sort of smooth decay of the loss function where the training is happening. And you can see that this two-dimensional data, two-layer perceptron can easily learn. That's the demonstration. Now, once we have trained the model, we need to store it. Like, what's the point of training if you can't store it and use it later? So the way to store the learned weight parameters are like accessing it as .state dictionary. Okay, so here you can see that if you want to see what are the learned weight parameters, you can just print the state dictionary and you can do a torch.save. So this will save a .pt file in your hard drive, which will store the learned weight parameters. And later, if you want to use that state of the neural network architecture, you just do a torch.load. And again, you can use this classifier to run, like, do evaluation from this trained network. Okay, so you can do a load state dictionary and you can access the weight parameters. Now, in a classification, how do you do an evaluation? You find out accuracy, like true, positive, false, negative, things like that. So here an accuracy parameter is computed. And here you see when you compute the performance of a neural network, that's when you are not updating the weight parameters. So you should always set the mode model.eval. Okay, this will ensure that the backpropagation is not there and the weight update is not there. So here we see the predictions and just it will predict a score. And wherever the scores are greater than 0.5, we call it 1. If it's less than 0.5, we call it 0. And we try to figure out what is the amount of correct prediction. So it's almost like this is round off to 2 digits, but apart from like with a short training, with this simple data set, you can gain high accuracy. Okay. And here you can see that on the dataset samples, I have tried some visualization that where it's trying to get the class 1 versus class 0, and it has correctly predicted. The interesting things will be if you populate somewhere in between the points, how efficiently it can predict. And I'm sure there will be inefficiency there. So visualizing the class boundaries, like the decision boundaries. So this is what someone asked, and I have given you a snippet that how do I visualize the decision boundary for this classification using a trained model, data set, and a label. So here you can see that the network has learned that the top right and bottom left, these regions are class 0, whereas a fat boundary across this diagonal, that's what it is learned as class 1. And this is the decision boundary it's learning. Okay, so similarly for other data sets, you can have other ways of complicated problem, other decision boundaries, right? And finally, if you do a training, you can use tensor boards in PyTorch, or there are other things called weights and bias and Comet logger, just to monitor the training. But I thought let's not make it too complicated. What I wanted to give you, like introduction to PyTorch tensor, how to compute Autograd, the optimizer, and how to write a model class like nn.Module and the custom data set. So these are the key components of PyTorch which you need to use. And I showed you like a full example of machine learning based simple classification, binary classification, that how to do a training and get the results out of it. So this is like starting from 0 to 1 toy exercise at full. Okay, so this is like an introduction to all basic major steps you need to know. And then we will see in person in the class that for graph neural networks, what you require. But this is the basic amount of PyTorch you need to know before you appear in person. So I wanted to give this introduction. So if you have questions, I will be happy to take.
So I have a question. So in the figure, you have shown that the descent boundary. Yeah, so in this figure, so why this descent boundary takes this diagonal, not the other diagonal?
What do you mean? This
I mean,
diagram?
the other diagonal means that the opposite case. I mean, you can also say that the descent boundary, like the
No,
cut
it's
in the
it's
positive
a
45 degree.
that's the human interpretation, but we want to know what is the decision boundary as was learned by the neural network. For this particular training, the decision boundary as the neural network figured out is this two different diagonal corners are two distinct regions but identical, and the connected diagonal on like left, top left to bottom right. This is another class. This is the decision which the neural network made. I could have done like, oh, this is one region and two left out. But that's like human eye inspection. We are interested in knowing how the neural network reached its own decision. And this is the decision boundary it reached.
Okay.
Any other questions? about how do we set up the training, the simple toy data set, the optimizer, the stochastic gradient descent. All of you should have access to the notebook. Please try to run the notebook and see if you have problems. Everything is
Sir,
clear.
hello.
Yes, I can hear you.
Yes. So should I have to install that iProgress in my environment or something? Because I'm getting an error in that training model step.
Which step?
iProgress training model. That's simple after the simple classifier, there is the definition of training model, train model.
This is the definition of train model, which
Yes,
I'm sharing.
yes. Here I'm getting an error running that after that train model. Next. There I'm getting an error that I progress not found. Please update IPY wages.
Oh, I think, yeah, if something tells you that not found, please install it. Probably you need to install it.
So IPY wages I need to install or
Let's see, widgets. Do I have widgets? Like in the first import, do everything worked properly for you? Like
yes.
Then probably if IPy widgets is not installed, you can just do pip install and it should install.
Okay. Okay.
Anything more? Otherwise, I will at least, like all of you have access to this code. So I'm stopping the sharing and but I'm open to take questions. Everything is clear with everyone?
So about the decision boundary, you showed that what neural network is identifying that the first diagonal is a cluster and the other two corner is the other cluster. So
Okay.
if my data was something like some data is in between, then it could have misclassified, right?
Correct.
So
So what you need to do, and you need to ensure that the data which you're using for the training is like IID with the data on which you're doing the evaluation. So if your training data doesn't have points in between, and certainly in your evaluation, you introduce points in the central region, then of course the neural network can't do the right job. Okay.
okay, but is there any process to identify those particular points or why
No,
that?
so you can so there are a few ways to debug. First of all, let's say for few points you see that there are misclassification or underperformance of the neural network. You can isolate them and try to study their feature patterns, like the x1, x2 coordinates, where they are. And you can go back in the training data and try to figure out whether there were points around that region or not. If not, then you surely know the neural network haven't seen points in that region and it doesn't know how to recognize them. So it's not trained to do that task. So obviously there will be underperformance. If that's not the case, you need to figure out what other features are causing this problem, and also take some points which are correctly classified to see what is missing from the correctly classifying objects, which are not there in the faulty ones, and vice versa. So this way you need to make some correlation plots in order to figure out what is the true problem with the problematic points, and then probably you can figure out a way.
Okay. So I installed the IPy wages, but still I'm having that same issue.
Can you just relaunch the notebook, start with fresh, and etc.?
Okay.
I mean, if this sustains, you can send me an email with a snapshot of what's the actual problem, and I will try to figure it out.
Okay.
Anything more? Any question, any doubts? Please practice PyTorch examples and also the notebook I have given you before coming to the school, because in the school it will be all like starting with graph neural network related packages, and there I will expect you to know all the basic things which I discussed today. Okay, so please try to go through them.
Hello, sir.
Yes.
Hello. So I have a nice question relating to this data set. Suppose in my data set, I have, let's say, outliers.
Okay.
So thing is that when we are feeding for the training, if my data set has an outliers, let's say many outliers, and if I'm feeding it for the training, so in the training, actually, I'm also adding some type of contamination, means the training will not. So my point is that, is it not a good idea that from the first data set, I determine what my outliers are. I throw those points and train the data.
Look, it's a good question. So first, let's see if you have found out some points are outliers, and let's call them junk, and you want to clean the data, then you can always do a pre-processing and clean your data. The important point is to apply the same pre-processing to your training, evaluation, and test data. As long as you're consistently doing it, it's a perfect thing to do. And most of the cases you want to do pre-processing, which helps the neural network to converge on its training faster. Saying that, there are other tasks, especially in high energy physics, something like anomaly detection, and where you want to find some rare outliers. Now, how you will pre-process your data in those cases is sort of tricky question. So for those cases, you need to be careful case by case, but in general, you're correct.
Okay, sir. Thanks, sir.